I'm going to talk a little bit about project, but I'm not going to talk too much about the propeller side. It's going to be more of a mathy side of this project. Not real math. I'm not a mathematician. I'm not even an amateur mathematician. I'm an amateurish mathematician, maybe, or a dilettante, or math poser might be better. There will be numbers. That's about all I should say. All right. So, some of you may have seen this rolling ball sculpture that I made. I just want to show this particular scene because it actually has 5 balls. I can actually get 5 balls on this thing on a good day. Today's maybe not the best day, but 5 balls is actually possible. So this device is powered by a propeller, P1, and that concludes the propeller portion of the talk. The real topic today is the shape of this track, this infinity symbol looking thing. So I called this sculpture Rhymes with Biscuit. And why did I call it Rhymes with Biscuit?
Because it rhymes with biscuit.
Yeah, I don't know if you can hear that, but this guy is a YouTuber, Matt Parker, a stand-up mathematician. And he did a video about this particular mathematical curve, which is called
Lemniscate, because it rhymes with biscuit.
So hence the name of my sculpture. This lemniscate looks like an infinity symbol. In this video, Matt Parker is actually talking specifically about the lemniscate of Bernoulli. That is this curve. And the lemniscate of Bernoulli has a very nice formulation in polar coordinates. In the upper left corner, you can see this is the equation. And if you plot that in Desmos, if everyone is familiar with Desmos, desmos.com, it's an online graphing calculator. It's super powerful. Anyway, this is the Bernoulli that's the lemniscate of Bernoulli. And if I had known about the lemniscate of Bernoulli when I was designing my sculpture, it would have saved me a lot of trouble. But I did not know about the lemniscate of Bernoulli. I didn't even know the word lemniscate at the time. So I had to make my own infinity symbol. And so when you, I don't know about you, but when I start a project, sometimes I don't finish the project. This may or may not resonate with some of you, I don't know. But I have a lot of projects that I have abandoned and forgotten. So when I started this rolling ball sculpture, I was kind of shocked to see, oh, I already did this. I discovered a forgotten project that I had started and abandoned to do this whole drawing an infinity symbol thing. And so there was this code that I had no memory of, but there was a gift from my past self, so that was nice. But when I looked at the code, it was incomprehensible and undocumented, and thanks a lot, past self. So it was. I had to try to reconstruct whatever my past self was thinking, and so that's basically what I'll be talking about now. So the lemniscate is this kind of figure 8 thing. My past self, or I'll just say I, approached it from the point of view of someone driving a car, across the desert, say. And how would you steer the car in such a way that the trail you left looked like an infinity symbol? All right, so that's the basis. So if you start in the center and head southeast, you're basically turning left. And when you get back to the center, you're turning right. And that's basically what you have to do. So as a rough start, just to get things started, here I have a little driving simulator, as it were. And I'm gonna, here's my simulated car driving a left 360-degree turn, followed by a right 360. And I mean, that's kind of a limniscate, kind of an infinity symbol. It's a start, but I'll just explain what the other parts of this screen are showing. The bottom half is a graph of the steering input function. The horizontal axis is the distance from the beginning to the end of the course. And the y-axis, positive values are a left turn, negative values are a right turn. And so this square wave says for the first half of the course, we're going to drive with the steering set at 12.5, whatever that is. And then for the right half, the second half, we'll turn right. And, and we have a little steering wheel here that says, oh, we're turning left now. And you can see the line going horizontally, showing where we are. So that's just a first cut. Right? We can do a little better than this, right? We can say, well, maybe we can drive straight through the intersection here instead of having these tangent circles. So something like this. If we plot this graph, you see we're going straight, we're turning left now, we're straightening out, now we're turning right, and now we're going straight again back to the center. I'll do that again, just so you can see. Watch the steering wheel. There's a sharp turn here to the left, and then straightening out, and then to the right, and then straightening up, and we're back. So it's looking closer to an infinity symbol, but the steering input function has a lot of these discontinuities, right? There are these stair step where the steering wheel you have to jerk the steering wheel abruptly. Probably not a very comfortable ride. So I was thinking, if only there were a function, a smooth, continuous function that starts at 0 and rises smoothly to a peak and then smoothly descends to 0 and then through to a negative peak and then smoothly climbs up to 0 again. If only there were such a function? If only. Anyone? Am I hearing sine function? Yeah. Yes, for the people at home, people on Zoom, the room erupted with a chorus of sine function. Yes. So yeah. So let's try replacing the stair-steppy steering input function with a nice sine wave. All right, so let's try this. Now the steering wheel, you can see, is a nice smooth turning, smooth motion. I don't have the amplitude quite dialed in right now because obviously the curve didn't close. You got to tighten up these turns a little bit. I just started with an amplitude of 14 here. Oh, I could have explained a little better here. For this first attempt with the 360-degree turns, the amplitude of this square wave is 12.5, whatever that is. That's 4 pi. 4 pi radians would be 720 degrees, meaning that if we maintain this steering angle for the entire duration of the course, we would describe a 720-degree circle. But since we're only going half the course of that steering radius, it does a 360, and then we switch over and do a 360 to the right. So that's what the amplitude means. So going back to the sine wave, amplitude of 14, obviously not enough, so we can bump that up to 15. Let me try that again. And it's a lot closer, right? And we can get even closer. Try 15.1. That's pretty close. We can make this a little bigger to kind of zoom in on the center there. It's pretty close to closing. If we make it 15.11, then I would call that closed. So 15.11 is our desired amplitude, our magic number. All right. So let's go back and make this a reasonable size. That's a pretty good infinity symbol, right? I think it's a pretty good looking infinity symbol. And around this time, we learned about the lemniscate of Bernoulli. So my wife and I started calling this the lemniscate of Park. But that number, 15.11, kind of magic, right? I mean, magic in the sense we don't really know what it means. At this point, I consulted the good folks at Metafilter. I don't know if you've heard of Metafilter. It's kind of that's an old school message board kind of thing. Anyway, Ask Metafilter is actually a great resource for getting answers to questions. So I went to my friends at Ask Metafilter and I asked them, I explained what was going on, and they're pretty smart there. They pretty quickly figured out that if you take 15.11 and you divide it by 2 pi, you get 2.4048, which may or may not mean anything to you at the moment, but if you're familiar at all with the Bessel function of the first kind, J sub 0, this is a graph of, the blue line is a graph of the function J0. The first root of J0 is right there, right about 2.4048. And in fact, Wolfram alpha will tell you as many digits as you like what the root is. It's 2.4048255, blah, blah, blah. So apparently my magic number depends on the first root of the Bessel function. And we're going to call that number 2.4048255. We're going to call that A because it's a mouthful to say, and we are going to see it again. So A, if we take A and then recompute our magic number, it's not 15.11, it's 15.1099. It's actually pretty close to 15.11, but now we have a more precise value for the magic number, because 15.11, we were just eyeballing something on a very crude simulation of a car driving around the desert. So this is neat. We're getting some actual numbers. And so another thing that Metafilter Smarty Pants were able to do was to put the lemniscate of Park into Desmos. And I guess it was one guy, he came up with this clever formulation as a parametric equation in T, where the X and the Y are these, definite integrals. It's maybe not as intuitively obvious what's going on, but it's mathematically much more elegant than that janky numerical integration thing I was doing. So this is super cool, I think. So he this into Desmos, and now I can also overlay the lemniscate of Bernoulli, and we can see how similar and yet different the two curves are. My lemniscate of Park is a little bigger in the vertical direction, a little thicker. If we if we were to zoom in tight on the origin, the red line is Bernoulli's lemniscate, and you can see that it's actually on the 45-degree diagonal and on the negative 45. It's basically, it's making a nice right angle at the intersection, nice 90-degree intersection. But the lemniscate of Park is not 90 degrees. It's a little bit bigger than 90 degrees. So what's going on there? Well, for the lemniscate of Bernoulli, you start out southeast, you come back to the origin, you have made a change in heading of exactly 270 degrees. And for the lemniscate of Park, turns out that the change in heading is 2 times A. Remember, A is our decimal, is the root of that decimal function. So 2 times A is 4.8 something. And if that's radians, if you convert it to degrees, it's 275.5727. So it's a little bigger than 270 degrees that you get in the lemniscate of Bernoulli. So that excess 5.5727 degrees gets put into the angle between the two lines there. So that's pretty. I mean, I don't know. Most of this stuff is actually above my head. I'm just kind of following along with what these metafilter guys were finding out, which is kind of cool. And there's one other thing about lemniscates that is of interest is the ratio of the perimeter, meaning the actual length of the curve. Choose a point to begin with and then loop around. That distance, the perimeter, what is the ratio of the perimeter to the half width of the lemniscate, right? We can sort of guess that like this quarter of the loop, it's obviously longer than the half width, but maybe it's 1.5 times longer than the half width, roughly, right? And there are 4 of them, so we can say that the ratio of the perimeter to the half width is going to be somewhere around 6 to 1. That's just a swag, but just to give you some idea of what the ratio is that we're trying to compute. So the ratio of perimeter to half width in the lemniscate of Bernoulli is actually an important number. That Matt Parker video that I showed at the beginning is not actually about lemniscates at all. He's actually computing something else, but he goes on this whole lemniscate side quest just to compute this ratio for the lemniscate of Bernoulli, and then he uses that ratio to solve his actual problem. So, I don't know if the perimeter to half width ratio in the lemniscate of Park has any use at all, but we're going to figure that out now. So turns out that in order to compute the ratio of perimeter to half width for the lemniscate of Park, you have to use a Struve function. This is apparently related to the Bessel function, even more abstruse. But there are a bunch of Struve functions. We are interested in h sub 0, the blue line here. If we evaluate h sub 0 at a, which is 2.4048, as you all remember, right about here, evaluate h sub 0, we'll see that that value is just about 0.75, roughly, right? And we can then ask. No, it's we're a little past the maximum. I mean, there is a maximum there, but we're a little beyond that. We're about here, I think. So we have to, we can eyeball a value of about 0.75, or we can ask, Wolfram alpha for the actual Struve function at that point, and it's 0.7497, which is actually pretty close to 0.75. So we take this value and we divide it into 4. We divide it into 4, we get the ratio of the perimeter to half width 4 over h sub 0 evaluated at A is about 5.335. So 6 wasn't completely out of the ballpark. So that ratio we can then use to figure out the half width of this. Where are we? Let's say this lemniscative arc, turns out has a perimeter of 2 pi. I was actually thinking, because the parameter t goes from 0 to 2 pi, I thought, oh, that's why the perimeter is 2 pi. I mean, the perimeter is 2 pi, but it's not actually the case that just because a parameter goes from x to y, that means that the perimeter, it just happens to coincidentally be 2 pi. Anyway, the perimeter is 2 pi, and we can then compute the half width as being 1.17769. And so see here that it intersects the x-axis at 1.177. And using that number, we can plug that into the formula for the lemniscate of Bernoulli so that it has the same half width. Because otherwise, the lemniscate of Bernoulli can take out any size, but we want it to be the same size. So now they're both, here they are side by side. Well, not side by side, but one on top of the other. They're well, that's basically it. So the lemniscate arc I claim as original because or my past self came up with it, but I don't know if it's novel in the sense that someone else may have already come up with it, and so maybe some math people, maybe here or online, can tell me that, oh, that's a well-known curve. Anyway, but before that happens, I just like to give a shout out to my Metafilter peeps for doing the numerical heavy lifting. And thanks to Ken and Chip and Parallax for this fun shindig. Thanks to my lovely, long-suffering wife who still supports my propeller-powered misadventures. And thank you all for your attention. I'm happy to entertain any comments, questions, or concerns.
And we have a gift for you.
Oh my goodness.
Since we gave you this pain of an ass table that was not level, and you really needed a level table, I got you a level.
Oh my goodness. Thank you.
So you can be level. I don't know how you can level the table, but it might
Thank
help you
you.
in the picture.
Actually,